Welcome back. In this video, we are going to look at problems of chapter 19b from your Atkins text. Before we proceed further, let's go through a quick recap of lecture 19b. In this video, we have discussed about the flux of X component of the momentum, which is nothing but the retardness of the molecules. And in that respect, we also defined a constant called coefficient of viscosity that describes the retardness of the movements of molecules in a solution. We also discussed its temperature dependence uh, with this equation right here with this equation. And we also looked at the movements of ions in an electrolyte solution. So we applied the phenomenological equations to not to neutral species, but also to the ionic species. In that respect, we also discussed about a law called independent migration of ions. Further, we derived few equations that to calculate the drift speed and mobilities of ions and how they are connected related to the conductivity. And further, we also derive the equations that connects the diffusion coefficient to mobility and drift speed of the ions. And these are commonly called as Einstein relations, of which the important one is the Stokes-Einstein equation, which relates the diffusion coefficient of ion to its hydrodynamic radius A or the Stokes radius. So first, let's discuss few discussion problems before going to the mathematical problems. The first question here is, discuss the difference between the hydrodynamic radius of an ion and its ionic radius and explain why a small ion can have a large hydrodynamic radius. Let's take a look at crystal structure of lithium chloride. Here the green balls represent chloride ion and the gray balls represent the lithium ions. The ionic radius is assigned based on the distance between ions in the crystalline form of the compound. I found a video on how to calculate ionic radius from its crystal structure, and the link is given here. If you want, you can go through it. So basically, the ionic radius is it's calculated based on the distance between the ions in its crystalline form. On the other hand, the hydrodynamic radius or Stokes radius is defined as the effective radius of solvated ion in a solution. Here, we talk about the total radius, including the hydration sphere, which means we also calculate the space that is occupied by the water molecules. So we can estimate the Stokes radius indirectly by measuring the diffusion coefficient of these ions, as both of these parameters are related as shown here in the Stokes-Einstein equation. The smaller ions like lithium have larger Stokes radius due to stronger electric field. Imagine the size of the lithium has the smallest size, but the charge to the surface area ratio is quite large for lithium when we compare it with rubidium. So that's why lithium plus ion attracts more water molecules. That means the hydrodynamic radius of lithium is larger compared to any other ions. Next question. So the next question here is, discuss the mechanism of proton conduction in water and how could a model be used to test this. So we discussed in the class that the diffusion of ions is very slow, maybe on the order of few micrometers per second or even per minute. Despite this, the conduction of charge by protons is pretty fast in water. And how is it possible? The conduction mechanism in water follows a rearrangement mechanism of its structure rather than diffusion mechanism. This is explained by Groth's mechanism. Imagine a protonated water molecule H3O plus, which is solvated by other water molecules. Let's imagine this is the H3O plus ion, which is sort of bonded or bonded to three other water molecules by means of hydrogen bond. And this, let's say that this is the first coordination sphere. So let's say this is the first coordination sphere. And these water molecules can further interact with other water molecules via hydrogen bonds to form a second hydrogen sphere. So all the green water molecules forms the second hydrogen sphere. However, the hydrogen bond strength in the second hydrogen sphere will be less compared to the first hydrogen sphere. From this, it is speculated that one of the hydrogens from the second hydrogen sphere will undergo a bond cleavage. Let's say this hydrogen is connected to some other water molecule in the bulk of the solution. Let's say one of this hydrogen gets cleaved. And what happens next is this free hydrogen will induce some structural rearrangements in the water molecules network. So, and that gives us a different structure which might look as follows. And here the total charge we are talking about is H5O2 plus. And there are only two water molecules in the first hydration sphere compared to the second hydration sphere, to the first structural rearrangement. So while this happens, it also induces the formation of another structural rearrangement, which is similar to the first one. So the first one had uh, had a molecular formula of H9O4 plus, and the second one has H5O2 plus. So this structure will again induce some other structural rearrangement in the water molecule, so that we are back to H9O4 sort of arrangement. H9O4 plus sort of arrangement. So it goes from here to here. So if you look at the position of the positive charge, in the first scenario, the positive charge was on oxygen, and the second scenario, the positive charge is on hydrogen. That means, let's say, this has moved from uh, oxygen to hydrogen. And if you compare the second and third scenario, again, the proton positive charge is moved from proton to oxygen here. So this thing happens. The time it takes for the transition time for each of this step is around 1 picosecond. So this is pretty fast. And if you combine them all together, from the bird's eye viewpoint, it looks as if the proton is hopping from one molecule to the other molecule as depicted in this figure. So the overall appearance is as though the positive charge has moved from point 1 to the endpoint at some infinity. So that's why the proton conduction is very fast in water. And how can this model be tested? So this can be tested by increasing the pressure of the system that we are studying. The molar conductivity of protons seems to increase with increasing in with increase in, temp, in with increase in pressure as the hydrogen bonds rupture with increasing pressure. So if you increase the pressure of the system, the hydrogen bonds or the strength of hydrogen bond decreases. Once the strength of the hydrogen bond decreases, the more the protons can move around so that the rearrangement reaction is pretty fast now, which is seen in terms of increased molar conductivity. So that's how we can validate the Grotthus model of proton mechanism in water. Going to the next question. Why is a proton less mobile in liquid ammonia than in water? So for this one, we have to consider the properties of a solvent or a solution, which is viscosity. So we have seen previously that the mobility increases as the viscosity or the coefficient of viscosity decreases. So let's compare the coefficient of viscosity values for both ammonia and water. So the viscosity for ammonia is given as 0.276 times 10 power negative 3 at negative 40 degrees Celsius, whereas for water it's 0.891 times 10 power negative 3 at 25 degrees Celsius. So by the look of these two values here, it almost uh, we might conclude that the proton is less mobile in water because of its high viscosity compared to the proton, which is kind of the opposite fact that we are asked to answer for. So we need to look at alternative mechanism how this happens. So in the last problem we discussed about the Groth's mechanism for the conduction, proton conduction in water. So where we consider the central molecule to be H3O plus, whereas in the case, and the same thing can be applied to the ammonia solution or liquid ammonia, in which case we have to consider NH4 plus ion. So this is not very intuitive, but it seems if there is a strong hydrogen bond that's present between the molecules, as soon as a proton from the second hydrogen sphere breaks, cleaves, it immediately induces the structural rearrangements because of the high hydrogen bond strength. So in the case of water, such hydrogen bond strength is very high, which means there is a lower activation energy for the molecules to rearrange themselves. Whereas if you compare it with the hydrogen bond in ammonia, they are weaker. This should be wrong. They are weaker in ammonia, and it's lower, and hence it might require higher activation energy to induce the structural rearrangement. So which and this activation energy might not be available by the thermal energy. So that's why the mobility of proton is less in liquid ammonia than in water. So far we have discussed about three discussion questions, and from now on we will look at the mathematics problem solving. So, so the viscosity of water at 20 degrees Celsius is 1.002 centipoise and 0.7975 centipoise at 30 degrees Celsius. So we are given viscosity of water at two different temperatures. What is the energy of activation for the transport process? We need to determine the EA, the energy of activation. One equation we have looked at earlier is this one, where coefficient, the temperature dependence of the coefficient of viscosity. From this, we can calculate the activation energy. So if any problem is given, as usual, so list down all the values that it's given. So we have the coefficient of viscosity at two temperatures in centipoise, and at two temperatures, I converted them to Kelvin to make it standard units, and to find the activation of energy. So we can take natural logarithms on both sides of this equation on the right. Then it becomes ln eta is equal to ln eta naught plus EA over RT. Since I have two different viscosities at two different temperatures, I might label this as ln eta sub T1 is equal to the eta naught remains constant because it's a constant, it doesn't change with temperature, plus EA over RT1. Let's say this is equation 1, and the second equation is ln eta sub T2 is equal to ln eta naught plus EA over RT2. Let's call this as equation 2. And I'm going to subtract 2 from 1. So it becomes ln eta T1 minus ln eta T2 is equal to EA over R, because ln eta naught gets cancelled. EA over R times 1 over T1 minus 1 over T2. So we need to find the activation energy. So let's take this to the left hand side of this equation. So EA is going to be, and I can rewrite this term as ln eta sub T1 over eta sub T2, the whole thing uh, divided by uh, 1 over T1 minus 1 over T2 and times R. So now we know the necessary equations. We know all these parameters, so we just need to plug in, which will be 8.3145 is the R value with gas constant times natural logarithm of viscosity at temperature 1 over viscosity at temperature 2. So remember, you don't have to change the units for the viscosity. Since both of them are in centipoise, the units gets cancelled. Divided by the temperature in Kelvin, 1 over 293 minus 1 over 303. So just do the math, you should be able to get the answer as 16.8 joule per mole. Make sure you know how to calculate these units. Let's look at the next problem. The mobility of a chloride ion in an aqueous solution at 25 degrees Celsius is given as 7.91 times the 10 power negative 8 meters squared per second per volt. Calculate the molar ionic conductivity. So what's given here? We know the temperature, the mobility of the chloride ion is given, and the Faraday is a constant, 96,485 coulomb per mole. So one equation that relates the uh, ionic conductivity to the mobility is this one. So it's pretty much a straightforward problem where we need to plug in the values. So lambda is equal to Z is charge. Here the charge on the chloride ion is -1, but we use the just the magnitude and not the sign. So Z is 1. So 1 times the mobility is 7.91 times 10 power negative 8. Again, make sure that you write the units times the charge 96,485 coulomb per mole. So if you do this math, you should get 7.63 times 10 power negative 3. But what about the units? So we need to work on calculating the units. This is a bit tricky. We need to have a good understanding of how each of these units are derived in the first place. So the mobility, the units of mobility is meter squared per second per volt, right? Times the Faraday constant coulomb per mole. I can convert the coulomb. So basically, 1 coulomb is equal to 1 ampere second. So I can rewrite that as meter squared per second per volt times ampere second per mole. And here, this seconds, 1 second gets cancelled with the other, these two. What's remaining here is meter square per volt ampere per mole. And by the definition of a Siemens, 1 Siemens is equal to ampere per volt. So this is nothing but Siemens. We are going to get the final equation as Siemens meter square per mole. So, so the answer would be 7.63 times 10 power negative 3 Siemens meter square per mole. So this should be your answer. The next problem. The mobility of a rubidium ion Rb plus in an aqueous solution is 7.92 times 10 power negative 8 meters square per second per volt at 25 degrees Celsius. The potential difference between two electrodes placed in a solution is 25 volts. So imagine there are two electrodes in the solution, rubidium Rb plus solution, which have a potential of 25 volts across the electrodes, and the electrodes are 7 millimeters apart. So what is the drift speed of rubidium plus ion? So we need to calculate the drift speed. What's given in the question? 25 degrees temperature, converted that to kelvins. Mobility is given. The potential difference is 25. Distance between the electrode is 7 millimeters. One equation that we know that relates, that connects the mobility and the drift speed is S is equal to UE, where S is the drift speed, U is the mobility. And here we don't know the electric field between the electrodes, but E can be calculated from the potential and the distance between the electrodes. It's nothing but the potential over the distance between them. So using these two, we can calculate the drift speed of the ion. So let's do that. So here, as I said, S is equal to UE. Instead of E, I can write it as U times del pi over L. Let's do the math. The mobility is 7.92 times 10 power negative 8 meters square per second per volt times 25 volts, that is del pi, divided by distance. I'm going to convert the millimeters into meters. Then it becomes 7 times 10 power negative 3 meters. If you do the math, it should get 2.83 times 10 power negative 4, and the end will be, the units will be meter per second. So volts get cancelled, per volt and volt, and 1 meter it gets cancelled. So at the end we get meter per second. If you want to rewrite this in terms of micrometers, it will be 283 micrometers per second. Let's look at the next problem. The limiting molar conductivity of sodium iodide, sodium nitrate, and silver nitrate are 12.69, 12.16, and 13.34 millisiemens meter square per mole, respectively at 25 degrees Celsius. So what is the limiting molar conductivity of silver iodide at this temperature? So we are given the limiting molar conductivities of different electrolytes, and we are asked to find the limiting molar conductivity of an unknown electrolyte, which is silver iodide. So I listed all of the paraphernalia that's provided in the question, and we know one equation, that is the law of independent migration of ions, and how each of the ion contributes the overall limiting molar conductivity, lambda sub m naught. So based on this, we're going to solve this problem. So let's rewrite the molar ion conductivity for each of these electrolytes in terms of law of independent migration of ions. So the first one, say here, lambda of sodium iodide, I can write this as, let me explain this equation. So the nucleus uh, determines the number of cations, and lambda plus is the what type of cation we are dealing with. So maybe like sodium plus as an example. Nu minus is the number of uh, anions that are generated from each molecule of electrolyte, and lambda minus is the type of anion which is iodide example, as an example. So I can write this as, from sodium iodide I get only one of these ions, so it's lambda Na plus lambda I minus. So that's the first equation. I can similarly rewrite the other equations, lambda m and NaNO3, then it's equal to lambda sub Na plus lambda sub NO3 minus. And the third one, lambda m of silver nitrate is equal to lambda sub Ag plus lambda sub NO3 minus. So this is, at this point we need to, it is similar to Hess's law where we need to combine these equations, solve these equations mathematically so that we are left with one equation that resembles the, that gives the molar ionic conductivity of a silver iodide. AgI is equal to lambda Ag plus lambda I minus. So how do we proceed from here? So if you look at this, we, in this final equation, we have Ag plus and I minus. If you look back at these two equations, Ag plus is coming from equation 3 and I minus is coming from the equation 1. So for sure, we know that we have to add 3 plus 1. But if we add 3 and 1 together, we are also contributing the conductivities from ions such as nitrate and sodium. So we need to subtract this. So if we add these 3 and 1 and subtract 2 from this, we can negate the contributions from sodium and nitrate. So the overall equation is going to be 3 plus 1 minus 2. And so it's going to look like sodium Na plus lambda I minus plus lambda Ag plus lambda NO3 minus lambda Na minus lambda NO3 minus. So at this point we have sodium gets cancelled, nitrate and nitrate gets cancelled. In terms of mathematics, we have 12.69 for sodium iodide and 13.34 for sodium nitrate. From this, we can subtract the contributions from sodium nitrate, which is 12.16. So the limiting molar conductivity of silver iodide is equal to, try and solve it. So if you solve this one, so you should get the answer as 13.87 millisiemens meter square per mole. So if an unknown, if the question gives you the molar limiting molar conductivity of different electrolytes and asks you unknown electrolyte, so we need to follow this procedure. Remember, sometimes a solute, an electrolyte like MgCl2 will give two chloride ions only and only one magnesium ion. So in that case, your lambda, this equation looks like lambda Mg 2 plus 2 times lambda Cl minus. So you need to incorporate such equation in case if you get electrolytes that gives multiple ions. Next question. At 25 degrees Celsius, the molar ionic conductivity of lithium plus, Na plus, and K plus are given here in terms of millisiemens meter square per mole, respectively. So we need to find what are their mobilities. So one equation that we know that the molar ionic conductivity is related to the mobility. So we are now, in this case, we are given the ionic conductivities. We just need to find the mobilities. So we just need to rearrange this equation so that mobility is equal to lambda over ZF, where Z is the charge. And Faraday is 96,485 coulomb per mole. So it's just straightforward equation that you plug in the lambda, that is the molar ionic conductivity for these three different ions, and Z is positive one, just one for all of these ions, and you should be able to get the answers as the mobility of lithium ion is 4.01 times 10 power negative 8 meter square per volt per second, and that of uh, sodium is equal to 5.19 times 10 power negative 8, again meter square per volt per second, and the mobility of K plus is equal to 7.62 times 10 power negative 8 meters squared per volt per second. That's a straightforward question. Going to the next question. Estimate the effective radius of a sucrose molecule in water at 25 degrees Celsius, given that its diffusion coefficient is 5.2 times 10 power negative 10 meters squared per second, and that the viscosity of water is 1 centipoise. Sometimes the examiner enjoys giving the questions in terms of confusing units. 1 centipoise is equal to a hundredth of a poise, and 1 poise in terms of kilo is equal to zero point 0.1 kilogram per meter per second. I hope your examiner allows you the cheat sheet so that you can have all these conversions in a paper. Otherwise, you need to remember all of this. So here, the question asks to calculate the effective radius of sucrose molecule in water. That means we have to calculate the Stokes radius or the hydrodynamic radius A, and the diffusion coefficient is given for us. So one equation that relates the diffusion coefficient and the hydrodynamic radius is the Stokes-Einstein equation. So let's rearrange this equation so that the A is on the left side. A is equal to KT over uh, diffusion coefficient times 6 pi eta. So the coefficient of viscosity eta is given as 1 centipoise, but we need to convert that into SI units. So 1 centipoise is equal to 1 times 10 power negative 2 poise, which is equal to 1 times 10 power negative 3 kilogram per meter per second. I guess we have sufficient information. We just need to plug in all these values in the equation. So K here is the Boltzmann constant, which is 1.381 times 10 power 23. I might be wrong. It's V negative 23 joule per Kelvin times 298 Kelvin. That's the temperature divided by the diffusion coefficient 5.2 times 10 power negative 10 meters squared per second times 6 times 3.14 times the coefficient of viscosity 1 times 10 power negative 3 kilogram per meter per second. Since you know all these values, you just need to plug in everything. Solve it, you should get 4.2 times 10 power negative 10 meters, or in terms of picometers is 420 picometers. So that's the effective radius of one sucrose molecule in aqueous solution. Another simple question. The mobility of a nitrate ion in aqueous solution at 25 degrees Celsius is 7.4 times 10 power negative 8 meters square per second per volt. Calculate its diffusion coefficient in water at 25 degrees Celsius. So we know the temperature and mobility, and one equation that relates the mobility to diffusion coefficient as is D is equal to URT over ZF. So basically we need to calculate D, and again it's a straightforward equation. let's plug in all the details. So D is equal to, the mobility is 7.40 times 10 power negative 8 times the gas constant 8.3145 times the temperature 298 Kelvin divided by the charge is on the nitrate ion is 1. Again, as I said previously, we just consider the magnitude and not the sign, times the Faraday constant 96,485 coulomb per mole. You should get the answer as 1.90 times 10 power negative 9. Again, follow the units all the way, so you should end up getting meters square per second. So let's look at our larger questions. When I say the questions are larger, but the answers are relatively straightforward and simple, at the most, we might have to use an Excel a spreadsheet to calculate the answers. So the viscosity of benzene uh, with the temperature as shown in the varies with temperature as shown in the following table. So this is the coefficient of viscosity of benzene at different temperatures in Celsius. So we have to use this data to infer the activation energy for viscosity. So how do we solve this problem? So we have seen already how the viscosity is dependent on the temperature. So ln eta is equal to ln eta naught plus Ea over RT. So this equation is similar to the linear fit, which is in the form of y is equal to A plus mx. So if we can plot ln eta uh, ln eta versus 1 over t, then the slope is going to be the Ea over r, where slope is equal to m is equal to Ea over r. The intercept A is equal to ln eta naught. But what we need is just what we need to find is the activation energy Ea. So I considered these values given in the question. I converted the Celsius to Kelvin and Kelvin to 1 over K, because we have to plot 1 over T and not the temperature. And the same way, I took the values for eta and then converted them to ln of viscosity. So I get these values. And I just plotted the graph between 1 over T and the ln eta as shown here when I used Excel spreadsheet to calculate this. And I fit a trend line for all these points to get a linear fit equation. So again, it's the same graph here. The slope from this equation, which is this one, right? This mx plus c, m is m, the slope is equal to Ea over r. That's equal to 1221.7. Again, we need to find Ea. Ea is equal to 1221.7, and the slope we get slope in terms of Kelvin times the gas constant 8.3145 times joule per Kelvin per mole. If we do this math, we should get 10157.824 joule per mole, because the Kelvin and Kelvin gets cancelled here. And writing the same thing in terms of kilojoule per mole, approximately it's going to be 10.2 kilojoule per mole. So this is how you calculate the activation energy. In general, consider doing an experiment like this. You measure the viscosity of any solvent or solution at different temperatures. Once you get the data, you can calculate the activation energy for each of this movement of molecules using the same procedure. Let's go to the next question. The conductivity of aqueous ammonium chloride at a series of concentrations is listed in the following table. Deduce the molar conductivity and determine the parameters that occur in core law. So At different concentrations of ammonium chloride, the experimenter has calculated the conductivity, measured the conductivity. So what we need to find is the molar conductivity, which is the lambda m, and determine the parameters of the Kohlrausch law. So the molar conductivity is related to the conductivity by means is by kappa over C, where C is the concentration, K is the conductivity, and Kohlrausch law we know it's lambda m is equal to the limiting molar conductivity at infinite dilution minus K, which is a constant, times the square root of the concentration. So again, I check this data that's given for us. If you had observed the difference between units, the concentration is given in terms of dm cube, and the kappa is given in terms of centimeters. So we need to make it common units all across the parameters. So I changed the concentration mole per dm cube to mole per meter cube. I just have to multiply it by 1,000. At the same time, I took the kappa conductivity and then converted that from millisiemens per centimeter to millisiemens per meter. Again, here I have to multiply the value by 100. And again, from concentration, I took the square root to calculate the square root of the concentration. And from the kappa value and the concentration value, these two values right here, I calculated the molar conductivity based on this equation. Again, I used the spreadsheet formula to just calculate that real quick. So once you get, that's the molar conductivity for each at each of these concentrations. So if you look at this Kohlrausch law again, this is in the form of A plus mx. This is the linear fit. So we can plot between lambda m and the square root of the concentration. So I did that using Excel, and then I did a linear fit across these points, and I get this equation where slope of this equation is minus 2.5722. So minus k is equal to minus 2.5722. K is equal to 2.57, and the units are millisiemens meter square and mole per dm cube to the power of negative 3 halves. And the intercept is lambda m naught, which is equal to 12.78 millisiemens meter square per mole. So this is how you can calculate the limiting molar conductivity at infinite dilution and the Kohlrausch constant K if we were to now measure the conductivity of solutions of different concentrations. Again, this is also one of the experiments if you come across at any time in your study. Next question. Conductivities are often measured by comparing the resistance of a cell filled with the sample to its resistance when filled with some standard solution, such as aqueous potassium chloride. So the conductivity of water in terms of millisiemens per meter at 25 degrees Celsius, and the conductivity of 0.100 mole per dm cube KCl solution is 1.1639 Siemens per meter. A cell had a resistance of 32.21 ohms when filled with 0.100 mole per dm cube concentration of KCl, and 300 ohms when filled with 0.100 mole per dm cube of acetic acid solution. What is the molar conductivity of acetic acid at that concentration and temperature? So what's the question is asking is, if you take a cell with electrodes, positive and negative, and if you fill this electrode with solution, let's say KCl, the cell resistance, the resistance of the cell, let's say it's given by some R1 value. And if you change the KCl solution with acetic acid, it gives another value, which is R2. So the resistance of the cell depends upon the concentration and the type of electrolyte we use. If you are given one resistance of one of the cell under one solution, we can calculate the resistance of the other one. So we have to use these parameters to find the molar conductivity of acetic acid at that at particular concentration and temperature. So I've noted all of the values that are given for us. We are given kappa value of conductivity of water, 76 millisiemens per meter, and that of KCl is 1.1639 Siemens per meter. Again, make sure that you read the question and read also the units properly. Here, the conductivity is given in terms of millisiemens per meter. Here, it's Siemens per meter. So converting that to millisiemens, it's going to be 1163.9 millisiemens per meter. And the resistance of KCl solution at 0.1 concentration is 33.21 ohms. And that of acetic acid at the same concentration is 300 ohms. We have to find the molar ionic conductivity of acetic acid. So one thing we know is by the definition, kappa is equal to L over A times R. R is the resistance. So I can rewrite this as kappa is directly proportional to 1 over R, right? Because the length between the electrodes and the area of the electrodes remains constant for a given cell. So L over A is constant. By the way, L over A is also called as the cell constant because it depends on the geometry of the cell. Imagine if you have a solution of some ions, it could be K plus Cl minus or acetate ions. The total measured conductivity is a contribution both from the water and the ions, right? So so I can take the conductivities of acetic acid. I can take the ratio of the conductivity of acetic acid to the conductivity of KCl solutions, and I can rewrite this as contribution from both acetic acid and water, and contribution from both water and the KCl solution. Since, as I mentioned earlier, kappa is directly proportional, or inverse resistance is inversely proportional to the conductivity. So if I were to rewrite this, it's going to be resistance of the KCl solution over resistance of the acetic acid solution. Since this is inversely proportional, we're going to flip the KCl and the acetic acid here in this term, and which is equal to 33.21 over 300. We know these values from the question. So what we need to find really is the conductivity of the acetic acid. So I'm going to bring this to the left hand side of the equation. I underlined these terms so that you can relate them. So I'm going to multiply this term with this numerical here. So kappa times kappa of conductivity of KCl plus conductivity of water times 33.21 over 300 minus this term conductivity of water. I know these values from the question. So it's 1163.9 plus 76 times 33.2 over 300 minus 76. If you do this math, you should get 61.2156 millisiemens per meter. So that's the conductivity of acetic acid. But the question has asked us to find the molar conductivity of the acetic acid. We know this equation how the molar ion conductivity is related to the conductivity. So kappa value we know, and the concentration also we know. You just need to divide these two, and you end up getting 612.156 millisiemens per meter per mole dm cube. Again, if you look at this one, it's in meter. This is in dm cube. You want to switch them into a common units. Let's do that into centimeters square. You end up getting 6.122 Siemens centimeter square per mole. Make sure that you practice how to convert the units. It's going to get tricky. As I said, some of the examiners would love to would love to confuse you with different kinds of units. Next question. This question is particularly long, so let's look at part by part. The resistance resistance of a series of aqueous sodium chloride solutions is given here. So they are formed by successive dilution of a sample. So let's say that you take a highly concentrated solution, then you dilute it with water. Again, you take this and then dilute it water so that you get different solutions of different concentrations. And the resistance, so the resistance of these series of solutions were measured in a cell with cell constant. The constant C in the relation like K is equal to, okay, I'll explain this in a bit. With cell constant that is equal to 0.2063 centimeter inverse. The following values were found. So we have to verify that the molar conductivity follows Kohlrausch law and find the limiting molar conductivity. So let's solve the first problem, then go to the other one. So as mentioned in the previous problem, we know this relation where kappa is equal to L over RA, right? And I said L over A is something called as the cell constant. So we can write this as C over R, where C is the cell constant. The cell constant depends upon the type of the cell, electrochemical cell that we use. And here in this case, C is equal to 0.2063 centimeter inverse. We all know that the limiting, the molar conductivity is related to conductivity as kappa over C. So I can substitute this value in here so that it becomes C over RC. Again, don't get confused between these two different C's. The uppercase C is the cell constant and the lowercase c is the concentration. So once we know this, at this point we can calculate. First thing we have to do is we need to find the molar conduct. But we have to verify that it follows the Kohlrausch law. As we know the equation for Kohlrausch law is molar conductivity is equal to limiting molar conductivity minus K constant times C power half. We need to prove that this data follows this equation. Again, I took this data and resistance. I calculated the square root of concentration from the concentration, and I calculated the limiting the molar conductivity using this relation C over RC. So once I know the lambda m and C power half, I plotted them using a linear fit as we did in the previous problems. So the trend line fit gives me an equation y is equal to mx plus c. We need to deal with some of these uh, equations. Let me go back. So I forgot to mention one other thing. You need to be careful on how you get these units from this relation. Right, let's look at these units real quick. So we know that the molar conductivity is equal to kappa, or it's the cell constant over resistance times the concentration. So the units for cell constant is per centimeter inverse and resistance is ohm. And the concentration is mole per dm cube, right? I'm going to rearrange these so that I don't, taking the negative powers off. So it's going to be dm cube over rho times mole times centimeter. Let's convert this into meters. So if I were to convert this, it becomes 1 times 10 power negative 3 meter cube over ohm mole times 10 power negative 2 meters. Again, solving the math, we should get 1 times 10 power negative 1. 1 over ohm is Siemens by definition, so it's Siemens meter square per mole. and I converted Siemens to millisiemens so that it's 1 times 10 power 2 millisiemens meter square per mole. So that's how I got this equation, the units for the molar conductivity. So once I got this molar conductivity and CF, I plotted them, and then as usual calculated the slope. The slope, the limiting molar conductivity is given by the intercept, right? So which is 15.842. Again, make sure that you know what units you have to write. It's millisiemens meter square per mole, and the constant K is equal to 8.3971 millisiemens meter square mole per dm, uh, the whole term to the power of 3 halves. These are the units. So this is the first part. We need to figure out the other parts as well. So we have to use the value of K that we just calculated, which should depend only on the nature and not the identity of the ions, right? So on the information that lambda Na plus is and lambda minus ionic conductivities are given here, and we have to calculate the molar conductivity and the resistance it would show in the cell of 0.01 mole per dm cube concentration of sodium iodide at 25 degrees Celsius. It's relatively straightforward to do this at this point. We know that the Kohlrausch law is limiting lambda m is equal to lambda m naught minus K C half. So the limiting molar conductivity of sodium iodide is nothing but the contributions from the individual ions, right? So the values, the ionic conductivities. So we just have to add these two, which is 5.01 plus 7.68 minus the K value 8.3971 times the square root of the concentration, which is 0.010 per half. So if you just do that math, we get the molar conductivity as 12.69 minus 0.8397, which is equal to 11.850 millisiemens meter square per mole. So this is the molar conductivity. The second question, so this is part A. The second question asks for conductivity. So we know del M is equal to kappa over C, and kappa is equal to C times lambda M. So it's nothing but I converted, okay. So we are given here in the previous slide, the concentration is 0.010 mole per dm cube. If you convert that into mole per meter cube, it's going to be 10 mole per meter cube times the molar conductivity 11.850. We have to do this because the molar conductivity is in terms of meters. So the final answer for conductivity is going to be 118.50 millisiemens per meter. What about the third one? We need to find the resistance of the cell when we use this solution. So the resistance is given as, when we know from the previous in as we solved in the previous problems, kappa is equal to C over RC, right? We need to find R. So I'm sorry, this is not this is not copper. This is the molar conductivity. So we know this value. So now R can be uh, written as C over C lambda, or nothing but it's C over kappa. So the C value here we had was 0.2063 centimeter inverse, but I'm converting that to meters since our kappa is in terms of meters. So it's going to be 20.63 meter inverse over 118.50 millisiemens per meter. So the resistance is going to be 174.09 ohms. Make sure that you convert the millisiemens to Siemens here, since ohm is defined, 1 ohm is equal to 1 over Siemens and not millisiemens. Try solve this problem, you should get 174.09 ohms as the resistance of the cell. So this is what question has asked, and we have solved almost the entire question. Let's look at another problem. What are the drift speeds of lithium, sodium, and potassium in water when a potential difference of 100 volts is applied across a 5 centimeter conductivity cell? How long would it take an ion to move from one electrode to the other? In conductivity measurements, it is normal to use alternating current. So what are the displacement of the ions in centimeters? Solvent diameters about 300 picometers uh, during a half cycle of 2 kilohertz applied potential difference. Okay, the question seems complicated as we continuously read, so let's break it into different parts. First, let's calculate the drift speeds. We know one equation where the drift speed is related to the mobility and the electric field, and the electric field can be calculated from the potential and the distance between the electrodes, as we solved in one of the problems. So that should be a straightforward one. If you calculate E first, which is 100 volts over 5 centimeters, this one will give us 20 volts per centimeter. And you can calculate the drift speed for all of these. You should get the answers as drift speed for lithium is 80.2 micrometers per second, and drift speed for sodium plus is 104 micrometers per second, and that of potassium plus is equal to 152 micrometers per second. So one thing to note here is look up the value of these, the drift speeds. So the ion moves approximately like 80 micrometers per second. So that's very slow, right? If you imagine if the vessel is like 5 centimeters apart, how long does it take to move from one to the other? Exactly, that's what we need to calculate. And see how the drift speed is changing with increase in the size of the ion. As we go from smallest lithium to potassium, the drift speed is increasing. But why do you think so? The size of the ion is increasing. We expect that the speed should decrease with the increase in the size. But why is this happening? Just give a thought. We will look at this issue and the last problem. It would be more clear then. But guess an answer for now. So we calculated the drift speed, and we need to find the time it takes to move across these electrodes, right? From going from one to the other electrode. So time is given by the distance divided by time. So the time for lithium is the distance is 5 centimeters. Let's convert that into meters. 5 times 10 power 92 meters divided by the drift speed, 80.2 times 10 power negative 6 meter per second. So if you do this math, you get approximately 623 seconds. So it almost takes, let's say, approximately 600 seconds divided by 60 seconds. So it almost takes 10 minutes to go for each ion to go from one electrode to the other electrode. And if you continue to solve the the T for other ions, you get the answer as for T of time that for the sodium ion to the time the sodium ion takes to move from one electrode to the other electrode is approximately 481 seconds, and that for potassium is 329 seconds. So the time is also decreasing as the size of the ion increases. Right, we need to look back at the question. What does it say? So we've calculated the times, and now in conductivity measurements, it is normal to use the alternating current, right? What are the displacements of the ions in centimeters? So in the conductivity measurements, we don't use the direct current, so we use the alternative current, right? It alternates between positive and the negative cycles. So we need to calculate what is the displacement of each ion during the alternating current. So for that, we need to understand a little bit of we need to do a bit of calculus. So let's make an equation for distance or the displacement. Let's consider the first half cycle, okay, from 0 to first half cycle. 1/2 nu, where nu is the frequency. And the displacement is nothing but the speed times the time, the change in time, right? S times S dot dt. So we know that the drift speed S is given as ue dt, and the equation for any alternating current, let's say E, is given as E naught times sine over 2 pi mu t, where E naught is the amplitude, which is the square of this one, and the alternating current changes with like a sinusoidal wave with the frequency nu and the time t. So we can substitute this equation for E in the integral. So the overall equation is going to be d integral 1/2 nu times u e naught sine 2 pi mu t dt. And these two are constants. So u e naught times 0 to 1/2 nu integral sine 2 pi mu t dt. So this is a standard integral, and if you solve this, try to solve it. If you solve it, you get the answer as u e naught over pi nu. So the displacement is equal to u, which is the mobility, times the e naught. I'm assuming that the amplitude of the alternating current is 20 volts divided by the pi 3.14 times the the frequency of the hertz as given in the question is 2 kilohertz, 2 times 10 power 3 hertz per second. If you calculate this, you end up getting 3.18 times 10 power negative 3 times u, and the units for this one is volts centimeter, volts second per centimeter. But we have to calculate the displacement in terms of centimeters, right? In terms of centimeters. So if you want to get the distance displacement in terms of centimeters, and you have to input the mobility u in terms of centimeter square per volt per second. I've already given the mobilities here, right here. So I'm going to, you can use these values to calculate the displacement d. And if you do that, the displacement for lithium is equal to 12.8 nanometers, and that of sodium is equal to 6.5 nanometers, and that of potassium K plus is equal to 24.2 nanometers. So this is how for each half cycle of the alternating current, the each ion gets displaced by 12 point, lithium ion gets displaced by 12.8 nanometers. And the third part of it asks how many uh, solvent diameters is this distance equal to. Let's say that let's consider H2O, a water molecule, to be spherical, whose diameter is approximately equal to 300 picometers. 300 picometers is equal to zero point 0.3 nanometers. If you divide this distance over 0.3 nanometers, that would be equal to approximately 43 solvent diameters. So it moves by that much. And for sodium, it's going to be equal to 55 solvent diameters. And for potassium, it's going to be 81 solvent diameters. Again, try to pause the video and then try to explain why do you think as the size of the ion increases down the group, why the displacement or the speed increases for these ions. All right, this is a last problem that we're going to discuss in this video. Estimate the diffusion coefficients and the effective hydrodynamic radii of alkali metal cations in water from their mobilities at 25 degrees Celsius. Estimate the approximate number of water molecules that are dragged along by the cations. And ionic radii are given here as right here. So the question asks us first to calculate the diffusion coefficient and the effective hydrodynamic radius, that is A. If this is the ionic radius of lithium ion, the effective radius is going to be the outer circle, which also considers the water molecules that are attached to the ion. So we need to find that first. So it's easier. So we know one equation, that diffusion coefficient is related to the mobilities U by this equation. And for all these cations here, the charge is positive, 1, just 1. So plug in these values to calculate D. So gas constant is 8.31145. T is the temperature. I'm going to leave the mu as such so that we can put different mu's use here to calculate the diffusion coefficients for different ions. So this is the equation that you get. So this is the equation you get. You can replace U with different mobilities, and the final answer you should get in terms of centimeter square per second. Similarly, for the hydrodynamic radius, we get this. We already have this equation, right? Where the hydrodynamic radius is related to the mobility U. Again, if we do the math here, you should get this form of the equation, and the hydrodynamic radius is in terms of meters, or you can rewrite that in terms of picometers. So once you calculate, I've used Excel to calculate these values, but I get the diffusion coefficient here and the hydrodynamic radius. All right, as the size of the ion increases, the diffusion coefficient is actually increasing and the hydrodynamic radius is decreasing. So now you should be able to tell why the mobility was increasing as the size of the ion increases. Even though the ionic radius increases down the group, the effective hydrodynamic radius actually decreases down the group. We have also discussed this in one of the previous questions. The charge to the surface area, the ratio of the charge to the surface area for lithium ion, which is the smallest ion, is quite larger when compared to the rubidium plus, since the positive charge is still 1, but the rubidium has a higher surface area so that it effectively decreases the electric field around the charge. Since the electric field is stronger for smaller ions, they attract more water molecules. So that's why their hydrodynamic radius is larger compared to those of larger ions, Rp plus. And I've also got the ionic radii from the crystallography data. where the ionic radius increases down the group, right? Which is kind of expected. So I can calculate the volume. So what we need to find is how many molecules of water are dragged by each of these ion. For that, I need to determine the volume that of just the ion. I hope the marker works. I need to calculate just this volume, and also have to calculate the volume that comprises the entire water molecules, right? Let's say this one. So if I subtract this area from this volume from the entire volume, it gives me the volume of water. So if I have to calculate the volume of the outer sphere, for that I need to consider the hydrodynamic radius. So the volume based on the hydrodynamic radius is given by 4 over 3 pi a cube, and that of the inner sphere, which considers the ion. All right, where are we? So I can calculate the volume based on the hydrodynamic radius and also from the ionic radius by these two equations. Here I use the hydrodynamic radius and here is the ionic radius. And if I subtract one, 2 from the 1, I can get the volume of water, right? So volume of water is equal to 4 over 3 times pi times a cube minus r sub plus cube. So let's calculate for lithium for one. So for lithium, the delta volume, the change in the volume or the volume of water is equal to 4 over 3 times pi 283 cube, which is the hydrodynamic radius in terms of picometers, minus 59 picometers times 10 power negative 36. Basically, I'm converting the picometers to meters. So the change in volume is the volume of water is given as 5.56 times 10 power 20 negative 29 meter cube. I can do the same thing for sodium plus, where I used 184 and 102 for hydrodynamic radius and ionic radius as given here in the table. And I get the volume of water to be 2.16 times 10 power negative 29 meter cube. So imagine each water molecule to be a sphere with a radius of 150 picometers. So I can calculate the volume of one water molecule as 4 over 3 times pi times 150 cube times 10 power negative 36, right? Because we are converting that to meters. So the volume of one water molecule is 1.4 times 10 power negative 29 meter cube. If I divide the volume of water that I got from the previous calculation, the delta V from here for lithium, and divided by the volume of water, I get approximately 4 molecules of water. So which means each lithium ion is surrounded by 4 water molecules. So when lithium ion moves in the solution, it also drags 4 water molecules along with it. Whereas for sodium, it only drags the 2 molecules. So again, why do you think so? The electric field, the charge concentration on lithium plus is much greater than on the sodium plus. So lithium attracts more water molecules than the sodium. So this is one way we can calculate the number of water molecules that are the hydration sphere, basically. Thank you for listening, and I will see you in the next video with problems on chapter 19C.